Dear students, today we are going to discuss about light emitting diode. Light emitting diode we usually see in several places in decorations, specifically in electronic devices. So today we are going to discuss about what is LED and how it works. Let's go to the topic. Basically the LED is basically known as an optical semiconductor device. What it will do is it will convert that electrical energy into light energy. So in this process, what will happen to supply the electric current to the PN junction diode initially. So it will convert whatever the energy we are supplying, that will convert to the light energy due to the recombination of charge carriers. This conversion of electric current to the light energy is known as the electroluminescence effect. So this LED works in the principle of electroluminescence effect. So LED is normally a PN junction diode. I usually know what is PN junction means. A P is a P-type semiconductor, N is a type semiconductor. If you combine both P-type and N-type semiconductors, it will form a junction at the middle due to the diffusion process. That will form a PN junction. PN junction is known as it is a combination of P-type and N-type semiconductors. If we connect a PN junction in forward bias, means positive terminal to the P-type semiconductor and negative terminal to the N-type semiconductor. If you connect the uh, bias like forward mode, so what it will do is the free electrons, whatever there in the N-type region, it will it will enter into the junction region, the same as the holes which are majority carriers in P region. It will enter into the junction. At the junction, what will happen is when the positive hole and negative electron will come close together, it will get recombined. Whenever the electron and hole will get recombined, it will release its energy in the form of light. So in LED process, LED device, it has to be connected in forward bias mainly, so that the free electrons in the N-type region or a conduction band and holes in the valency band or P-type region, it will get recombined at the junction. So it may, while recombination, it will release its energy in the form of light. So that is how the LED will flow if we connect in forward bias. So this is a symbol. Of a LED diode. It is a normal PN junction. Here you see the light arrows which are drawn upward direction. It means it is emitting. It is emitting light. The PN junction which is emitting light is known as LED diode. If the same lines are drawn towards the diode, it means it is absorbing the light. But here the lines are drawn upward. It means the LED is emitting the light. So let's see construction of an LED diode, how it will construct. It is constructed by, as I told you, that PN junction, P-type and N-type semiconductors. So the first N-type layer is coated on the substrate. Over that, this is an N-type region. It is coated on the substrate. It is a metal substrate. Over N-type region, over N-type semiconductor. The P-type semiconductor is coated so that the contact region of N-type and P-type semiconductors due to the diffusion process, and a junction will form. It is nothing but a diffusion layer will form that works as active region in LED device. So on upward again, one metal substrate will be fixed due to the because of for the reason of ionic contact. So now, if you see the construction of LED, see the N-type semiconductor is coated on substrate. Over that, the p-type semiconductor is coated. The between of p-type and n-type semiconductors, there is a region. It is here denoted by white color. This region is called an active region. It is formed due to the diffusion process. It is depletion layer we call usually at the junction. And the junction also we call. This region, whatever the region, it is formed due to the diffusion process between p junction, p-type n-type semiconductor and p-type semiconductor. Here the recombination will takes place if we connect in the forward bias. So whatever the light is emitting when it is connected to the forward bias in this region, it will emit light. So this is the construction of LED as we see. So if you see clearly, we can understand easily the construction of LED. See here, it is the substrate. Aluminum metal contact is given below. Over that, highly doped highly doped N-type semiconductor is coated. Over that, P-type semiconductor is coated. The middle between P-type highly doped N-type semiconductor and P-type semiconductor, the region was formed due to the diffusion process. Here, it is indicated with red color. It acts as an active region in LED device. Over that, again, one aluminum metal contact is given to conduct the charge carriers, which are to conduct the electric field. So this is the construction. See here, if we connect the forward bias, see here the positive charge is coming to the p-type semiconductor and negative charge is coming in n-type semiconductor. So what will happen? Whatever the positive charge it is given to the p-type semiconductor, it creates a repulsive forces in the p-type semiconductor, so that what it will do, whatever the holes are there in the p-type semiconductor, it will push us towards the junction. The same way the negative charge is given to the n-type semiconductor, here it experiences a repulsive force. So whatever the electrons are there in the n-type semiconductor, what it will do, they will push it towards the junction. So from n-type semiconductor, the electrons will come to the junction, and from p-type semiconductor, the holes will come to the junction. So once the electron and holes are coming are in the junction, in the middle of the junction, what they will do, they will get recombined. As we know, whenever the conduction band electron is combined with the valency band hole, so what it will do, it will release the energy in the form of light and heat. For direct band gap materials, if you see, it will release light as a output energy. If you see indirect band gap materials, there for every recombination, it will release heat as a output. So here for LED fabrication, we have to choose a direct energy band gap material, so that whatever the energy they will release while the recombination must be in the light form. So it is a optical light device. So we will choose the direct band gap materials. So this is the construction of LED. You can see. So working as I discussed, whenever the forward bias is connected to the PN junction, whatever the majority carriers are there in the p-type and n-type semiconductors, here p-type semiconductor holes are the majority carriers. In n-type semiconductor, electrons are the majority carriers. What they will do, if we supply the forward bias to connect the forward bias to the PN junction, all the holes enter into the n-type region, all the electrons enter into the p-type region. So here, while the entering the, if you see the particularly electrons, if they are entering to the p-type semiconductor, p-type region, here the holes are the majority carriers, and whatever the electrons is coming from the n-type semiconductor are the minority carriers. It seems like we are injecting the minority charge carrier. We are injecting the minority charge carriers in the p-type semiconductor. The same way, whatever the holes are there, it will enter into the n-type semiconductors. Here, n-type semiconductor, the majority carriers are the electrons, and the holes are coming from P region, they will enter into the entire region. Holes will be the minority carriers. Here also it is seen like this. We are injecting the minority carriers as a holes in entire cell. This process is called minority carrier injection. So whatever the excess carriers of the minority carriers, whatever there is somewhere, after crossing the barriers, they will also they will be combined. They will be combined in a radiative recombination occur. Here also the minority carriers of electrons will be combined with the holes. Radiative recombination. So this is a bar diagram of the LED. You see, this is a p-type semiconductor. This is the n-type semiconductor. The valency band and conduction band. The electrons and holes are combining at the junction. While recombination happening at the junction, it will release its energy in the form of light energy. So this is the process will happen in the LED. It will convert the electrical energy to the light energy. So now we know how the LED will flow, or what is the phenomena mechanism happens in the LED. The LED has to be LED is basically just to recall other things, few things. The LED is basically a PN junction device, a diode, and it has to be connected to a forward bias. Once the forward bias is connected, whatever the majority carriers are on both sides, what they will enter into the junction. Where at the junction, what they will do, they will get recombined and release the energy in the form of light. So if we consider the direct band gap semiconductors, they will release the light as an output energy. If you mostly we will choose the direct band gap materials because LED is an optical device, it has to emit the light. So we will choose the direct band gap materials preferably. So we can choose the material according to their band gap to emit certain colors. So based on this equation, Ag is equal to Hc by lambda. Basically, equation is E is equal to Hc. Means for C by lambda. Okay. Now, according to this equation, based on this equation, we can find the band gap for corresponding colors. If we want to fabricate red color LED device, we will substitute the red color wavelength here. We will get particular wavelength, and we can choose the wavelength of semiconducting materials, which is in the range of this energy gap we are getting by calculating this. So according to this, accordingly, we will choose the semiconducting materials to fabricate our choosing colors. So this is a pictorial representation of LED. So you can see the epoxy lens and by reflective cavity here. The semiconductor, whatever the PN junction is placed here, and it is connected to a LED frame, flat spot. These are the connections I will calculate. So this is a picture. It will be like this. For infrared color, if you want to fabricate, we have to use a gallium arsenide as a semiconductor. If you want to fabricate a red to infrared orange colors LED, we have to use the gallium arsenide phosphide for this to acquire these colors. If you want to fabricate a bright red, orange, and yellow colors, this aluminum gallium arsenide phosphide is a combination of semiconductors we can use to obtain these colors from LED. For red, yellow, and blue, we choose the gallium and phosphide semiconductors to obtain these red, yellow, and blue colors. Aluminum gallium phosphide semiconductor will give the green color. Gallium nitride semiconducting material it will emit green, emerald green color. Gallium indium nitrate, it will emit near your UV and the blue colors. Zinc selenide, this semiconductor is used in the blue semiconductor. Aluminum gallium nitrate, it will use ultraviolet radiation. So these are the construction and working of it. See the applications of it. The application we see in several decorations, in roadside indicators. We can see that electrical signals. In biomedical applications also we can see, lab-oriented programs also we can see. If you see United cities, entire cities work with the LEDs. Now we can see, we know very well that LED TV. Now we can use our LED lights for sensing and lasing applications. This is normal lights we use at home. And these are the applications of